Hello everyone. I welcome you to join us on a heroic journey through a labyrinth of mathematical physics. My name is David and I will be your guide as we explore the structure of E8 and try to explain what it is good for in theoretical physics. In this video, we will discuss everything from Lie algebras, root systems, and obscure details of exceptional Lie groups to physics concepts such as spacetime symmetries, gauge symmetries for the standard model, grand unified theories, string theory, and how this all relates to unified field theories from E8. I'll try my best to introduce these concepts without assuming any prior knowledge. After reviewing some fundamentals, we'll discuss progress with E8 research from the past few years and months. Okay, so what is E8? To get started, the term E8 is not very specific as there is the E8 Lie group, the E8 Lie algebra, the E8 root polytope, the E8 root lattice, and the E8 Weyl group. Even this is not always specific enough, as the E8 Lie algebra has a complex form and 3 real forms. There is also the E8 Dickon diagram, but don't worry about this one for now. To get started on this exploration, we'll first review the foundations of symmetry groups, Lie algebras, and discuss how they are classified via the geometry of root systems. Lie groups, Lie algebras, and symmetry. A group is an algebraic structure that is closed under the operations of addition and multiplication, contains an identity element, each element has an inverse, and the group is associative. Matrix representations of groups are common as matrices can be added, matrix multiplication is associative, the identity matrix is well understood, and inverse matrices can be found if the determinant of the matrix does not vanish. Discrete groups provide some simple examples. For instance, consider 1x1 matrices or numbers. One of the simplest groups is Z2, which contains the identity element 1 and the reflection transformation -1. The reflection is its own inverse, as -1 times -1 is equal to 1. Since real numbers are associative, we see that this is a discrete group with 2 elements. Permutation matrices are another example of discrete groups. No permutation at all is the identity element, while permuting 5 elements 4 times is the same as applying the inverse permutation once. A Lie group is a continuous and differentiable manifold, which makes it a smooth geometric structure. A Lie group has a corresponding Lie algebra, which contains a Lie product that is anticommutative and associative. The Lie algebra may be n-dimensional with n independent generators. Since the Lie algebra is closed, the product of 2 generators leads to a linear combination of generators under the Lie product. The entire algebra is encoded by structure constants called FABC. For any matrix representation of a Lie algebra, the commutator as a Lie product automatically satisfies the Jacobi identity, since matrix multiplication is itself associative. The Lie algebra's multiplicative product is therefore not matrix multiplication A times B, but rather the commutator of A and B, which is A times B minus B times A. For instance, the commutator of TA and TB is equal to I times FABC times TC, where TA, TB, and TC are generators, and physicists often include a factor of I with the structure constants for convenience. Lie algebras also satisfy the Jacobi identity by definition. An example of a Lie group is the set of all real n by n matrices with non-zero determinant, called GLNR, or the general linear group of n by n matrices over the real numbers. All of the simple Lie groups can be found as subgroups of the general linear group of n by n matrices over division algebras, which include the real, complex, quaternion, and octonions. One of the simplest examples of a Lie algebra is U1, which is isomorphic or the same as SO2. We can consider SO2 as the symmetry of a circle in 2 dimensions. The SO2 group transformation admits an infinitesimal transformation that isolates the algebra's generator such that the group transformation G is equal to 1 plus theta times t if theta is infinitesimally small. Arbitrary SO2 group transformations can be implemented by a 2x2 matrix in terms of sine theta and cosine theta, which implements a rotation. Instead of considering SO2, the Lie group U1 has transformations that apply a complex exponential to a complex number. It is well known that complex exponentials are related to the trigonometric functions such as sine and cosine, which hints at why SO2 is the same as U1. The Lie algebra generator is found by an infinitesimal group transformation. The symmetry group of spheres in n dimensions, or the symmetry of Sn-1, is given by SON, as the rotation of any n-1 sphere gives back the same sphere. Real orthogonal n by n matrices act as generators of SON that act on the vector representation. Complex unitary matrices lead to the group UN, where setting the determinant of the matrix equal to 1 leads to SUN, which stands for special unitary group, which has n squared minus 1 dimensions. An n times n complex matrix has two n squared components, but a unitary transformation implies that the diagonals are real while the off diagonals are related and complex. By removing the single U1 generator associated with changing determinant, we see that UN is the same as SUN cross U1. For instance, SU2 has 3 generators given by the Pauli matrices, while SU3 has 8 generators given by the Gelman matrices, and so on. Quaternionic unitary matrices lead to symplectic groups, which have been used to describe phase space, such as position and momentum in physics. Octonionic unitary matrices lead to the so-called exceptional Lie groups G2, F4, E6, E7, and E8. Root systems and representations. Cartan and Killing realized that root systems classify the finite-dimensional simple Lie algebras. Root systems contain geometrical shapes called root polytopes that correspond to each Lie algebra. The vertices of the root polytope are called root vectors. Simple root vectors can be chosen to generate all of the root vectors by adding the simple roots together. For instance, A2 contains 2 simple roots alpha 1 and alpha 2, which can be added and subtracted to construct all 6 root vectors, forming a hexagon. The classical Lie groups correspond to AN, BN, CN, and DN, while the 5 exceptional Lie groups G2, F4, E6, E7, and E8 contain root systems with the same name. AN corresponds to SUN plus 1, DN corresponds to SO2n, BN corresponds to SO2n plus 1, and CN corresponds to SB2n. Well, actually, there are different conventions here, as some might refer to it as SPN. The root polytope leads to a notion of a root lattice, as the polytope can be translated by any root vector that is within the root polytope. The weight lattice is the dual lattice of the co-root lattice. Just understand for now that the weight lattice contains all of the representations of the Lie group and is closely related to the root lattice. So, what are representations? Einstein's special relativity represents spacetime events as a 4-vector of 3 spatial dimensions and 1 time dimension, which is a representation of the Lorentz group SO31, or its double cover spin 3, 1 for spinors. By focusing on the spin of massive particles in space, consider spin 3, which is isomorphic to SU2 for rotations. SU2 has various different dimensions for its representations, which includes 1, 2, 3, 4, 5, etc., which are all different representations. We refer to the odd representations as bosons and the even representations as fermions. For instance, a scalar particle such as the Higgs is trivial with respect to the Lorentz group and only has one spin state of spin 0. A fermion such as an electron has 2 spin states of +1/2 and -1/2. A massive spin 1 particle such as a W or Z boson has 3 spin states of 1, 0, and -1. A spin 3/2 particle has 4 spin states, and a spin 2 particle Think of a massive graviton would have 5 spin states at the classical level. In this sense, the SU2 group can act on these different representations. The one representation is trivial, which has no action from SU2. The 2 representation can be acted on by Pauli matrices, which are 2 by 2 unitary matrices, and is often called the fundamental or smallest non-trivial representation. Since 3, 4, and 5 are also representations of SU2, there are also sets of 3 by 3, 4 by 4, and 5 by 5 matrices that have the same structure constants as the Pauli matrices. While the structure constants might not literally be the same, they will be encoding the same algebra and can be transformed within each other and shown to be given the same root polytope. These different representations are classified by weight polytopes contained in the weight lattice. For AN, the n simplex and its dual is in the weight lattice. For instance, SU3 is described by A2, which contains a 2 simplex or an equilateral triangle with 3 vertices, just as a quark can have 3 colors of red, green, and blue. AN therefore relates to regular triangles, tetrahedra, and n simplices in general. The A2 root polytope is a hexagon, while the A3 root polytope happens to be a cuboctahedron. Both of these describe the close packing of spheres in 2 dimensions and 3 dimensions. For Dn, the n-orthoplex, which is a generalization of the octahedron, is found in the weight lattice, while the root polytope is given by the edge centroids of the n-orthoplex. The dual polytope of the n-orthoplex is the n-cube. The D3 root polytope happens to be a cuboctahedron, which can be thought of as a truncated cube. The Bn root polytope can be found by adding a Dn weight polytope to the Dn root polytope, since Dn is always inside of Bn. In this way, we see that B3 adds a 3 orthoplex or an octahedron to the D3 root polytope given by a cuboctahedron. Since B3 contains D3 and a weight polytope of D3, it can be identified that SO6 is a subgroup of SO7, where the octahedron relates to the 6 representation of SO6. It turns out that SO6 has 15 generators, while SO7 has 21. As such, we find that the 21 generators of SO7 break to the 15 representation of SO6 with the 6 representation of SO6 as well, where 15 plus 6 is equal to 21. While AN, DN, and EN all have roots of the same length, which are called simply laced Lie algebras, we see that BN contains roots of different length. The CN root polytopes are found by taking the BN root polytopes and switching their root lengths. It turns out that B2 coincidentally is the same as C2, but this pattern does not hold for large N. G2 looks like a seal of Solomon as a dressed Star of David. All of the exceptional Lie groups can project down to the G2 lattice with a commuting algebra in the center of the star. The E8 root polytope happens to be the Gaussian polytope, which is like an 8-dimensional generalization of a cuboctahedron. When 3D spheres are placed in a close packing arrangement, their kissing points form a cuboctahedron. When 8D spheres are placed in a close packing arrangement, the Gaussian polytope is found as the kissing points. In other words, the E8 lattice describes the most efficient way to pack 8-dimensional spheres. As mentioned, these root systems classify the Lie groups, but there is more to uncover. Precisely, these root systems correspond to the complex form of a Lie group or Lie algebra. Each Lie algebra also admits multiple real forms. They always have a unique compact real form and can have multiple non-compact real forms. Different non-compact real forms will have different numbers of compact versus non-compact generators. To understand the difference between compact versus non-compact generators, consider SO3 as the Lorentz group of spacetime. We can consider SO3 inside SO31, which is compact. This refers to the 3 generators of rotations in 3 dimensions, which contains sines and cosines. SO3 can be seen to be a compact group because if I apply a single generator successively, I will eventually come back to the same point after rotating by 360 degrees around a circle, or 720 degrees for spin 3 as the double cover. For SO31, there are 6 generators, which correspond to the 3 rotations of space and the 3 boosts of space-time. The boosts are mathematically found from hyperbolic trigonometric functions such as sinh and cosh. The boost can be thought of as increasing the velocity of a frame of reference, which can always be pushed closer and closer to the speed of light, yet never reach it. However, applying a single boost will never lead back to the same point as it did on the circle, which shows that SO31 has 3 compact rotations and 3 non-compact boosts. In general, SON is compact while SOP(q) is non-compact. E8 has 3 distinct real forms, named E8-248, E8-24, and E8-8. The physicists decided to make a convention to display the number of non-compact generators minus the number of compact generators in the subscript. Since E8 has 248 generators, E8-248 has 0 non-compact and 248 compact generators, which makes this the compact real form. E8-24 has 112 non-compact generators and 136 compact generators, which is sometimes called the quaternionic real form. E8-8 has 128 non-compact and 120 compact generators, which is often called the split real form. Semi-spin 16, which has the same algebraic structure of SO16, is a maximal subgroup of the compact real form of E8. When 2 groups have the same Lie algebra, it means that they only differ in their global or topological structure, but are the same infinitesimally or locally. The 120 degrees of freedom for SO16 leave behind 128 degrees of freedom within E8, which corresponds to the irreducible spinor representation of SO16. E8-24 contains semispin 12,4, while E8-8 contains semispin 8,8. For the rest of the video, I'll not go into the topological differences between SO16, spin 16, and semispin 16. Many physicists will sloppily refer to spin 10 as SO10 as they have the same Lie algebra, so I apologize if I make this mistake from time to time. SO16 inside E8 might motivate the idea that 16 times 6 by 16 real matrices could make contact with E8, but not quite. By considering 128 by 128 matrices, SO16 can act on the 128 spinor representation, while the adjoint representation of SO16 has 120 by 120 matrices. This motivates how E8 can be found in SO248 as 248 by 248 matrices. However, these matrices are somewhat unwieldy. I should also mention that the Gaussian polytope of E8 admits a discrete Hopf vibration of a 7-sphere with 24 cell fibers as a discretized 3-sphere, where a 24 cell is the root polytope of D4 corresponding to spin 8. Physics applications of Lie groups. Lie groups are essential for physics as continuous symmetries lead to conservation laws as discovered by Emmy Noether. We have conservation of angular momentum, which relates to rotational symmetry as a Lie group. Translational symmetry leads to energy momentum conservation, which can be formulated as an extra-dimensional rotation. Charge conservation of electromagnetism, the strong force, and electroweak theory motivates charge also as a form of some extra-dimensional momentum, which motivates the exploration of extra dimensions for understanding the conservation of all physical quantities. Gravity motivates Lorentz symmetry as SO31, while the Poincare group with translations can fit inside SO41 or SO32. The conformal group also is motivated for quantum gravity and unification, which is described by SO42 in D = 3 + 1. Electromagnetism has U1 gauge symmetry, while the electroweak sector has SU2 cross U1 symmetry. The strong force has SU3 symmetry, which leads to the standard model with SU3 cross SU2 cross U1 symmetry. All of the particles in the standard model are identified as representations of this gauge group. Their force carrier bosons are related to the action of the Lie group on the matter particles, which are often found in the so-called fundamental representations. Grand unified theories are studied with higher symmetry groups such as SU5 and spin 10. For instance, SU5 gut remarkably breaks to the standard model gauge group, which means that it not only contains SU3 cross SU2 cross U1, but it also allows for the 5-bar 10 and 1 representations to break to the representations for quarks and leptons with the right representations for SU3 and SU2 as the right weak hypercharges for U1. This is a subtle point, as the U1 in the standard model corresponds to this weak hypercharge, which has a lot of bizarre values. So it's quite remarkable how SU5 can capture these charges right away. The 3 2x2 Pauli matrices are related to the 3 W bosons of SU2, which can act on weak isospin doublets as a representation of SU2, while the 8 3x3 Gelman matrices are related to the 8 gluons, which can act on quark color triplets in the fundamental representation. This all helps encode the interactions of the standard model. The standard model is a chiral gauge theory, which means that left chiral vial spinners are commonly used to formulate this theory. A chiral or vial spinner is an irreducible representation of SL2C, which is isomorphic to spin 3,1, by the way, and these chiral or vial spinners are represented by a complex 2 vector. SL2C as complex 2x2 matrices can act on these complex 2 vectors to return another complex 2 vector, which shows how the 2 and 2 bar representations of SL2C relates to a single chirality of a particle and its antiparticle. A Dirac spinner is commonly studied in physics for the electron and its positron, which is a collection of 2 massive vial spinners giving a complex 4 vector. A massless Dirac spinner can also be found as an irreducible representation of SU2, where we see that the SU2, are complex 4x4 special unitary matrices that can act on a complex 4 vector, such as the massless Dirac spinner, which contains both the particle and its antiparticle of both chiralities. Our goal is to eventually understand if spinner representations for the matter particles can be combined with representations of the standard model within a single representation of E8. Octonions and E8 gut. Feza Gursey was a pioneer in applying exceptional mathematics such as octonions and exceptional Lie groups to physics. Witten stated that Feza Gursey was one of the most respected members of the physics community, and his untimely death on April 13, 1992, was a great loss to theoretical physics. Feza's scientific work is marked with remarkable originality and elegance, as well as intellectual courage. He never hesitated to pick problems that were not fashionable. Witten is referring to Gursey's bold conviction to explore quaternions, octonions, and exceptional Lie groups for applications in physics. Physicists are often only comfortable with real or complex numbers. Gursey and Koka pointed out that E3, which is equal to A2 plus A1 at the root lattice level, is used for the standard model with SU3 and SU2. They also noted that E4 is A4, which corresponds to SU5 and is the first gut model. E5 is the same as D5, which corresponds to spin 10 and is the first gut to unify a single generation of fermions into a single representation. E6 gut was introduced by Gursey, Ramon, and Sikovi and is the first in the E series that stands out as being its own unique root polytope and Lie group. Gursey had doctoral students that included Itzhak Bars, Pierre Ramon, Pierre Sikovi, Murat Günaydin, Metin Gürses, and Sultan Kato. Gursey, Gunaiden, and Kato have extensively discussed the role of G2 and the octonions in relation to QCD, as G2 is the automorphism group of the octonions. Now, let's not worry about what the automorphism group is, but just understand that G2 relates to the octonions. Studying G2 finds that SU3 is a subalgebra of G2 where the 14-dimensional G2 breaks into the 8-dimensional SU3 with the 3 and 3 bar representation left behind. This 3 is the fundamental representation for quarks, while SU3 can act on itself in the adjoint representation associated with the 8 gluons. It is as if G2 naturally contains the action of QCD with the gluons and a notion of a quark and an antiquark, without the Lorentz group vector and spinor representations for the quarks and gluons, respectively. Jeffrey Dixon and Cole Fury more recently have articulated how the tensor product of C cross H cross O can lead to a description of the standard model, which uses the octonions for QCD, or the strong force, and was inspired by Gursey's legacy. E6 gut was found to contain SO10 gut. Gursey inspired Bars and Gunaiden to develop E8 gut by 1980, which combined E6 with SU3F, where F is for family or flavor symmetry, as a description of 3 generations of matter. However, this E8 gut model requires a large 3,875 Higgs field and does not contain gravity. For this reason and others, E8 gut is not often studied. It is often claimed that only E6 can be used for gut, but this is not true, as Stephen Barr proved that chiral gauge theory can result from applications of E8 to 3 generations. The octonionic structure of these exceptional Lie groups is not perfectly understood either. For instance, recent work by Wilson, Dre, and Minogue discusses how to implement the E8 Lie algebra transformations with 3x3 octo-octonionic matrices, but the group transformations with octo-octonionic matrices have not been worked out yet to date. A book by Gursey and C provides hints, as this contains most details about F4 and E6 in relation to the octonions, but the scope of this textbook may have never been fully completed, possibly due to Gursey's death. Still, the understanding of division algebras has been helpful for the classification of supergravity theories, such as the magic pyramid of supergravities outlined by Mike Duff and collaborators, including Leon Borston and Mia Hughes, and others. It turns out that the number of supersymmetries found in supergravities theories, as well as the space-time dimensions, relate to the Freudenthal-Titz magic square, which formulates the exceptional Lie groups in terms of A tensored with J3O, where A corresponds to a division algebra such as R, C, H, and O for F4, E6, E7, and E8. I should also mention that J3O is the exceptional Jordan algebra, which are Hermitian 3x3 octonionic matrices. The number of supersymmetry generators is always equal to the dimensions of a division algebra such as 1, 2, 4, and 8, which for the higher numbers describe extended supersymmetries. The spacetime dimensions where supersymmetry occurs is always in 2 plus the dimensions of the division algebras such as 3, 4, 6, and 10. At least this is what most people think. While the Freudenthal-Titz construction of exceptional Lie algebras is beyond the scope of this video, just keep in mind that it is historically established how E8 mathematically relates to 3x3 octo-octonionic matrices, where this combines a tensor product of 2 octonions. E8 cross E8 heterotic string theory and E8 U-dualities in supergravity. While bosonic string theory is in 25 plus 1 dimensions and superstring theory with fermions is in 9 plus 1 dimensions, this all motivates some 16-dimensional space to account for the difference. To find the appropriate anomaly cancellations, string theorists Green and Schwartz realized that the self-dual 16-dimensional lattices lead to 2 options for such heterotic string theories, either D16 as SO32 or E8 cross E8. E8 cross E8 is a good option as it allows for breakings found from E8 gut. E6 cross SU3 is often generalized for the E8 cross E8 heterotic string theory. However, this video is mostly focused on E8, not E8 cross E8. M-theory was discovered by Ed Witten after attempting to prove that only heterotic string theory is natural, which ended up in resulting of a rediscovery of the 11-dimensional supermembrane theory. M-theory shows that all string theories are related by a web of dualities, hinting that some theory beyond M-theory could truly unify all string theories. The search for such a theory has been largely abandoned since initial progress by Bars and Sezgin from around 1997. M-theory has a two-brane, which is a generalization of a string. Membranes are extended objects, where a string is a one-brane, and a p-brane extends over p dimensions of space. In a 1996 conference proceedings, Martinek briefly outlined that E8-24 was relevant for a background-independent description of two-time M-theory, as the two-brane in 10 plus 2 dimensions motivates an auxiliary 2 plus 2 dimensions, adding together to give 12 plus 4 dimensions. Adding the Majorana-Weil spinor representation of 128 dimensions to spin 12,4 is the exceptional Lie group E8-24. By 1997, Bars followed by Sezgin showed that D equals 11 plus 3 contains a superalgebra that truly unifies all of the supergravity and string theory superalgebras in D equals 9 plus 1, D equals 10 plus 1, which includes type 1, type 2a, type 2b, E8 cross E8 heterotic string theory, and SO32 heterotic string theory, as well as the M-theory superalgebras. The conformal group of SO11-3 is SO12-4, which is the bosonic sector of E8-24 that removes that 128-dimensional spinor representation. Bars and Gunaiden also did important work on constructing exceptional Lie groups in terms of 5 gradings. A 5 grading is a separation of a group's generators into 5 different collections or grades. A 5 grading of E8-24 can be found by breaking SO12,4 to SO11-3 cross SO1,1 to give E8 as a 248 dimensions that are equal to representations in different grades, with 14 in one grade, a 64 spinor in another grade, the 91 plus 1 referring to the SO11-3 cross SO11 in another grade, another 64 spinor in a 4th grade, and finally another 14 in the 5th grade. These gradings are identified by the SO1,1 weights of each generator, which is a type of charge. Murat Gunaiden has worked on some mathematical physics results on E8 and E8-24 as well. These groups also appear in the concepts of magic supergravity as discussed by Paul Townsend, Sergio Ferrara, Alessio Morani, and many other collaborators. In general, E8 relates to the U-duality of some supergravity theories, which describes the charge space of extremal black holes that can form fundamental particles. 11-dimensional M-theory can be compactified to 3 dimensions on an 8-dimensional torus to give E8-8, while a different 8-dimensional Enriquez manifold can be used to give E8-24, which can be recovered from reducing 4-dimensional n equals 2 supergravity to 3 dimensions. However, the precise interpretation or the precise identification of the standard model without unobserved superpartners has remained elusive to string theorists. Standard model plus gravity. Garrett Lisi infamously released a paper on E8 in 2007. The paper had multiple issues. First, SO15,1 was mentioned, but this is not inside any real form of E8. This is not much of a problem, as SO15,1 is a Wick rotation of SO16. Second, the standard model typically contains 192 off-shell degrees of freedom for fermions if we're assuming Dirac neutrinos, but E8 only has 128 as a spinor representation, which is typically used for fermions. Later work from Lisi attempted to latch onto SO4,4 cross SO8 inside SO12,4 inside E8-24, and he tried to motivate this 192 degrees of freedom as a form of 64 plus 64 plus 64 via representations of SO44 cross SO8, such as 8 vector with an 8 vector of both and 8 spinner of both, because you can have an 8 spinner, an 8 chiral spinner, and 8 vector representation of SO8. And then we have 2 SO8s, so we get 8 times 8, giving 3 different types of 64, summing up to 192 in total. But this does not work to describe 3 generations of fermions, as the 8 vector, 8 vector representation must be associated with bosons. Also, E8 contains commutators, not anti-commutators, as it is not a superalgebra. It is often thought that a superalgebra is needed to bypass the Coleman-Mandula theorem, which discusses the types of symmetries that can be used for quantum field theory. Lisi's work is one of the most read papers on the archive, yet it was never published in a peer-reviewed journal. Tony Smith pioneered the application of Clifford algebras and CL16 to E8, largely on his mystical blog and the preprint website Vixra. While his work is often criticized as too numerological, Smith was highly knowledgeable of a wide range of mathematical physics, including gratings of exceptional Lie groups stemming from work from Bars and Gunaiden. Tony was a close friend to many of us here at QGR and recently passed away. Carlos Castro Perelman also discussed various aspects of E8, including a theory based on the octic invariant, which is a mysterious mathematical object unique to E8. He discussed E8 in relation to a 15-dimensional superspace and has been a pioneer of Clifford relativity, which relates to the work of Tony Smith. Towards a realization of Lisi's dream. I will formulate Lisi's dream as the following. Let us dream that it is possible to use a single representation of a real form of E8 and nothing else to encode gravity with beyond the standard model physics. Okay, so how would we do this? There are 3 real forms of E8. Gravity is slightly non-compact, while the standard model and guts are typically compact. This more or less isolates E8-24 as it is non-compact, yet still more compact than E8-8. While E8-8 allows for a type of petit salam gut unification with gravity that is vaguely similar to recent work by Krasnov on spin 7,7, or even the geometric unity theory from Eric Weinstein, I will focus on E8-24 as it allows for multiple paths to unify conformal gauge gravity with all of the most popular guts, including SU5 and spin 10. This is unique to E8-24. However, to restrict ourselves to Lisi's dream, as I formulated, we must find a way to get gravity inside E8, yet not use the large 3,875 Higgs representation used in E8 gut. This is why Lisi's dream is so challenging. E8 gut had no gravity and a huge Higgs, so we're trying to fit more physics into less mathematical degrees of freedom. However, our collaborators and I have found work suggesting that it can be done, even including 3 generations of matter. To start, we considered all of the embeddings of the Lorentz group and the conformal group with the standard guts. These include additional theories outside the scope of Lisi's dream, but provides a mathematical overview of the possibilities just to get started. Despite string theory's utilization of E8 cross E8, no string theorist had taken the time to exhaustively explore E8-24 phenomenology in this manner. Next, we're going to discuss some subgroups of E8 with applications for physical symmetries. These will include gauge groups for gauge theories and grand unified theories, as well as spacetime symmetries for theories of gravity. The standard model contains the gauge group SU3 cross SU2 cross U1, while SU5 grand unified theory was the first gut discovered. Spin 10 gut unifies one generation of fermions into a single 16 representation, which then fits inside E6 gut. For spacetime symmetries, the Lorentz group is given by spin 3,1, which is isomorphic to SL2C. The conformal group in D equals 3 plus 1 is given by spin 4,2, which is isomorphic to SU2,2. Starting with the compact real form of E8, the E8 gut model focuses on breaking E8 to E6 cross SU3, followed by spin 10 cross U1 cross SU3. E8 can also break to E7 cross SU2, as well as F4 cross G2. While E7 cross SU2 and E6 cross SU3 can break to the same subalgebra of E6 cross SU2 cross U1, none of these exceptional breakings contain non-compact spacetime symmetries. Focusing on the non-compact E8-24, we can break to semi-spin 12,4, which can break to spin 2,4 cross spin 10. This is curious as it contains the conformal group in D equals 3 plus 1, as well as spin 10 for grand unified theories. Additionally, spin 10 can break to SU5 cross U1, leaving behind the conformal group. Remarkably, E8-24 can also break to SU7-2 and SU3-2 cross SU5. Both of these can then break to SU2-2 cross U1 cross SU5. This gives us 3 independent paths to explore how conformal gravity can be combined with SU5 gut, which can then break to the standard model. I find SU32 cross SU5 the most interesting as it isolates 3 different conformal charts of SU22 cross U1 inside SU32, which can have applications for 3 generations of matter. There are also ways to break the Petit Salam gut group from spin 10, as well as some other paths from spin 12-4 that I didn't mention. There's further motivation for why E8-24 can contain 3 generations of the standard model with only 128 degrees of freedom instead of 192. The standard model contains Weyl spinners with 4 degrees of freedom for particles and antiparticles of a single chirality or spin. 2 Weyl spinners can be placed in a massless Dirac spinner of 8 degrees of freedom to combine particles and antiparticles of both chiralities. The standard model has 3 quarks to 1 lepton. The electron and neutrino are leptons, while there are 3 up quarks and 3 down quarks of different colors, giving 8 different charge configurations in total. Additionally, there are 3 different mass generations that have been found in nature, and multiplying all this together gives 8 for the Dirac degrees of freedom, or 2 chiral Weyl spinners, 8 for the different charge configurations, times 3, which all leads to 192 off-shell degrees of freedom or quantum degrees of freedom for the fermions in the standard model, assuming Dirac neutrinos. Distler and Garibaldi correctly refuted Lisi's paper by pointing out that if SL2C, which is isomorphic to spin 3,1, was utilized, then E8 cannot work for 3 generations as 192 degrees of freedom are needed. However, consider the 16 spinner representation of spin 3,3. It turns out that spin 3,3 has 3 different spin 3,1s inside of it. If we take a single massive 16 spinner of spin 3,3, we can encode 3 different mass parameters in the spinner, since the 2 extra time dimensions allow for 2 extra dimensions associated with energy, which is like mass. I had done work previously in the scattering amplitudes community that had used 6-dimensional spinners to encode mass in a similar manner, but nobody had used this method for applications to 3 generations of matter. The upshot is that a single 16-dimensional spinner can encode 3 generations of matter, each of which typically have an 8-dimensional spinner. 3 times 8 is 24, but here we are only using 16 instead of 24. Once we account for the electron, 3 down quarks, 3 up quarks, the neutrino, and all 3 generations with 6-dimensional spinners, we get 8 times 16 equals 128 instead of 8 times 24, which is 192. In this manner, if we find 3 charts of spinner representations via higher space-time symmetries, then 3 generations of matter can fit in 128 degrees of freedom instead of 192. Currently, we are exploring the phenomenology of SU32 cross SU5 as it contains 3 conformal charts, which may admit a new formulation of holography. The use of SU32 is a generalization of the conformal group for gravitational symmetry, which is similar to how spin 3,3 generalizes spin 3,1 for Lorentz symmetry. Others have recently been exploring E8 models, but E8 is filled with pitfalls due to its complicated structure. For instance, Wilson and Dre Minogue recently put out a model, but it was claimed that SL3R was to be used for the strong force. SU3 is not SL3R. There is a lack of consensus amongst the collaborators themselves if this is contained in the standard model or a slightly different model. Tejinder Singh and collaborators recently discussed an octonionic model using E8 cross E8, but the location of the weak hypercharge seems to be inconsistent throughout the paper. These could all be various typos, but having a paper on the internet that is free of typos is crucial for communication, as there has been so much controversy surrounding the physics of E8. Another problem with E8 is that it is not a superalgebra. Even if we use this trick of encoding 3 generations of fermions in the 128 spinor representation of spin 12,4, it is not clear if this can be used to give fermions, as the string theorists claim that superalgebras are needed. However, Piero Churini returned from retirement due to the excitement surrounding E8 and briefly worked with QGR. In his model, he constructed the Grassmann envelope to find a new E8 superalgebra. This is perhaps the final step in unlocking the physics of E8. This is the reverse of a process investigated by Bars and Gunaydin back in 1979, but this trick had never been applied to the exceptional Lie algebras to give superalgebras until very recently. While Piero worked through the compact form of E8-248, we have unpublished notes that construct the Grassmann envelope of E8-24 and are exploring unified gauge theories based on this mathematics. Beyond M-theory. String theory is now understood to be more fundamentally described by membrane theories, which were first introduced in supergravity. M-theory is in 11 dimensions and contains a 2-brane with a dual 5-brane. F-theory is in 12 dimensions and latches onto a 3-brane from type 2b string theory, type 2b supergravity as well. S-theory is in 13 dimensions, and a superalgebra has been found in 14 dimensions with a 3-brane and an S-dual 7-brane. S-theory was introduced by Bars as conformal M-theory, but this theory isn't discussed too much. Some are worried about the notion of extra time dimensions, but F-theory is commonly studied and also has 2 time dimensions. Furthermore, the conformal group has 2 time dimensions, which is commonly studied in the ADS-CFT correspondence. Mike Rios dubbed A-theory as the D equals 11 plus 3 supermembrane theory. Recently, I've been referring to E-theory as the D equals 12 plus 4 supermembrane theory that generalizes M-theory, F-theory, S-theory, and A-theory. If M-theory is the mother, F-theory is the father, and S-theory is the sire, then A-theory is the ancestor or ancestral theory. Just to have a little fun, E might stand for elder, exceptional matrix model, or emergent membrane theory. While E-theory is still also currently under development, we published the superalgebras for A-theory and D equals 11 plus 3, which are already in the literature, E-theory and D equals 12 plus 4, as well as a notion of monstrous A-theory and D equals 27 plus 3, and monstrous E-theory and D equals 28 plus 4, as well as a tower of superalgebras to infinite dimensions. While this theory appears to have nothing to do with quasicrystals, it may turn out that further development of this theory could help inspire the completion of the emergence theory, which we'll discuss next. As such, E-theory might help provide a bridge between string theory and emergence theory. Emergence theory. Emergence theory was coined by Clee Irwin, which is QGR's theory currently under development. This theory involves the application of quasicrystal mathematics, such as the Elser-Sloan quasicrystal with H4 symmetry derived from E8. It is understood that quasicrystals allow for a discretization of conformal holography. In this manner, emergence theory is poised to be a serious contender for a discrete formulation of unified field theory. Eric Verlin constructed emergent gravity inspired by thermodynamics and ADS-CFT holography following work of Bekenstein and others. Freund articulated for emergent unified field theory, but no mathematics was developed for this vision, where all forces were found to be emergent. Recent work by Latham Boyle and collaborators has demonstrated that quasicrystals have applications to discrete realizations of holography. We look forward to future work to see progress in this direction. Researchers at Quantum Gravity Research have been exploring discrete formulations of physics that lead to emergent spacetime, including methods from loop quantum gravity, causal dynamical triangulation, and causal set theory. The gap between string theory, loop quantum gravity, and causal dynamical triangulations might not be too large, as Lee Smolin has studied an octonionic matrix model, and recent work from the CDT founders sought to connect their formulation to string field theory. Marcelo Amaral, Ray Ashheim, and collaborators at QGR have published work that applies the formalism of geometric state sums to model sets for the study of emergent spacetime from quasicrystals. Fong and Clee Irwin have discovered a new three-dimensional quasicrystal called the Fig, as it is constructed with the Fibonacci icosagrid method. More recently, Dugan Hammock and the rest of the team have been exploring the relationship of the Fig to E8. It is now apparent that these quasicrystal geometries can lead to new quasicrystal Lie algebras, but this is additional work currently under investigation. In conclusion, the plethora of ideas discussed in this video is inspiring for the future of E8 in relation to the unification of physics. Whether E8 is used in heterotic string theory, some reformulation of Lisi's dream, supermembrane theories inspired by M-theory, or quantum gravity research's emergence theory, what seems clear is that more and more research will continue to find the value of E8 for applications in theoretical physics and unified field theory. I thank you for joining me in drinking from this fire hose of information. I hope it provided a balance of the fundamentals while also discussing recent progress from various research groups.